introduce. Um, I would first of all like to thank IIT Kanpur Student Chapter for providing me this opportunity to interact with the audience here. So I'll just share my screen. Is it visible?
Yes, ma'am, it is visible.
So good evening, everyone. Now, I'm going to talk about this how we can enhance the situational awareness for resilient operation of power grid. This presentation I have divided into basically four parts. So first of all, we'll see that how like modern power grids look like, and then what is situational awareness, why it is important, and how it can be achieved. So one of the important things to achieve this situational awareness is wide area measurement systems. So we will briefly see what is this wide area measurement systems, and then we'll see a case study where we have developed one method for situational awareness, for enhancing the situational awareness. So we'll see that in detail, and then we'll conclude. So it is if we compare power system with human body, it becomes quite easy to understand the power system. Otherwise, the power system is a very complex system. Okay. So it makes us easy to understand. So we can see that the generation, it has this power system has different parts. We can divide it into generation, transmission, distribution, and then at the consumer's end. Okay. So this generation, it is basically the same, you can consider it same as our heart works. So this generation is supplying the electrical energy to the entire system, and this electrical energy is supplied through the help of transmission system, which are like arteries in our body. And we can further divide it with the voltage level going down, we can divide it into sub transmission and distribution. So this is how the electricity is supplied to the whole power system. Okay. But when we are supplying, we have this complex system, so we need to monitor it also, and we need to be aware of what is happening in this system. So that purpose is being served by regional load dispatch center. So we consider regional load dispatch center as our brain. Okay, so it will work similar as our brain works. So it is monitoring each and everything in our body. See, if some disturbance happens, we immediately recognize it, that something is happening in our body. So these signals are coming and our brain is receiving that. So similarly, these signals are being received by regional load dispatch centers, or in India, like we have state load dispatch centers, regional load dispatch centers, and national load dispatch centers. So all this, there is a hierarchy maintained in this. So, but these dispatch centers, they are working as a brain for the system. So state load dispatch centers, they are working as a brain for the subsystems which are assigned to them. So this is how the power system works. Now this modern power grid, see, the conventional power grid were like we have only this fossil fuel based power plants, and which we were able to control easily according to our requirement. But now we are adding to this power systems, we are adding more uncertain generations like renewable energy generations, so solar power plant or wind power plants, so which are very uncertain. So though we forecast them, but this forecasting, it is not necessary that it will be so accurate, isn't? So these uncertainties are created by this source side also. And if we come to load side, then also we have quite uncertain loads, isn't? So we are adding to it in distribution side also, we are adding now the generation system. So rooftop solars are there in the houses, and they can inject the power into the grid also. So like we have now, we have types of loads which can act at some moment as source, at some moment as load also. So all these things, they are basically increasing the complexity of our modern power grid. So though it is becoming uh, it is becoming very facilitating also in the sense of like power generation, and loads also are very helpful to the system, but at times they can create problems also in the system. So to utilize them effectively, we need to monitor them very closely. So now we will see what is situational awareness. So situational awareness means you are constantly aware of the health of changing power grid conditions. So we are continuously monitoring. See, you can be aware only if you are monitoring that thing. So if we are monitoring the power grid conditions closely, then we are constantly aware that what is happening in the power grid. So if we call, see, in simple words, we can say that situational awareness, it means you are getting information, and then you are understanding the information. Once you are understanding the information, then you need to think ahead also that what will be the impact of this information. Okay, then so that you can pre-plan things, that if this thing happens, then what will you do or what steps will be taken. So you can also say, in technical terms, you can say that situational awareness, it means it can be it will be comprising of three steps. One is perception, second is comprehension, and third is projection. So perception is similar to like getting information, and comprehension means understanding that information, and projection, so you, based on that information, you are projecting something, that what could happen in future. So this all three steps comprises situational awareness. So now we'll see what is situational awareness in power grids. So when we talk about the perception, then we say what information, because we are getting the information, but we need to understand that what information is needed. So in power grids, we need frequency, voltages, power flows, and breaker status. So if we know all those things, we can monitor the entire health of our power system. Then comprehension. So comprehension means, now when we are receiving this frequency, voltages, power flows, and breaker status, so we need to understand that what it is reflecting. Okay, so we need to interpret them quite well. Then only we will be able to plan our future action. So if there is frequency violation or thermal limit violation, or is there any impact of interchange, so we need to see that if frequency is violating, then what could happen if we do not prevent this from this violation. Okay, so first of all, we need to interpret the information received, and then if something is happening, then we need to plan that what could happen if we do not take this action. So accordingly, we can plan our actions also. Now, why situational awareness is important? Because in the past, many events, many blackouts have happened actually. So this is how slowly we have realized that this situational awareness is very important if we want to increase the resiliency of our power system. So the first blackout, like, which is very popular, after that many research has been carried out to improve the security of the and stability of the system. So it was the November 9, 1965 Northeast US Canada blackout. And after analyzing this, the committee submitted that the system control centers should be equipped with display and recording equipment, which can provide the operator with as clear a picture of system conditions as possible. So initially there were no display arrangements. Now we have very big screens in the load dispatch centers, and they can easily monitor. And there are several screens actually, so they can easily monitor what is going on. But initially there were not this kind of display. So after this blackout, it was found that it is important to have display and recording equipment in the control centers. After that, the next blackout was in like July 1996, which actually forced us to think something about our system. So this was in Western US, and that time it was identified that system operator must effectively monitor and assess the state of the transmission and distribution systems. It they have to assess the state of the system quite frequently. Okay. After that, on August 10, 1996, again a blackout happened in Western US, and the committee then it reported that it is important to train operators to be aware of system conditions and changes, and they develop displays that give them immediate information on changes in status. So that is how the evolution of modern load dispatch center has been there. Again, the the next bigger blackout is was on August 14, 2003, which affected both Northeast US and Canada. So that time it was identified that this blackout happened because we do not have adequate situation awareness. So from that time itself, this term has become important. So you can see this older version. So this figure shows you the earlier times of energy management system. So there's no display. All these were analog meters. Okay, so it was there. But now you see that how we have evolved. Our load dispatch centers or energy management systems, they are having these big screens, and they are monitoring this system regularly. So this, why it is important? If we have situational awareness in the system, or we are able to enhance it, then we can ensure security and reliability of power grid by facilitating decision making. See, if you are able to monitor the system, then only you can understand what is happening and you can make the decision also. And so it will assist in identification and implementation of corrective actions also. So now, how situation awareness can be achieved in power grids? So we can have, obviously we need to have measurement system, but we have different substations. So at different substations, these measurement systems are placed. So we need to have these measurement systems in place, and then we need to communicate this measurement data to the control center also. So we need to integrate measurement systems and communication technology in power systems. So this is one requirement. The second requirement is, nowadays when we are talking about the smart grid, so we are placing many sensors throughout the grid. So these sensors, they are continuously measuring the data, and this data is being transmitted to the control center. So a lot of data is coming there. So we need to integrate some information technology also, because when you are getting a lot of data, you need to process that information. Okay. So to achieve situational awareness in power grids, we need to integrate measurement systems and communication technology, and as well as information technology to process the information carried in a large number of measurements. So earlier we were having like supervisory control and data acquisition systems. So there the measurements were coming through RTUs, and the main problem there was they have limited grid visibility because the measurement data was coming at a slow rate. So it was like 2 to 4 seconds. Every 2 to 4 seconds, we were receiving one data, one set of data, you can say, and that too. So within 2 to 4 seconds, actually, a lot of things can change in the system. So they were not able to capture that dynamics also. So that was the problem. Then now we have this wide area monitoring system. So you can see here, this is the our picture of one of the load dispatch centers, and you can see that they are monitoring each and everything here. Even this renewable power generation is also being monitored. Every interconnected lines, how much is the power flow, how much is the generation, everything is being monitored here. So, and this PMU measurements, you must have heard about phasor measurement unit, which are providing the data at a very high sampling rate. So they provide higher speed scan rates, and that too with time stamped measurements. So that time is also synchronized with the help of GPS systems. So that is considered to be more accurate, and because the higher speed scan rates are there, so it is enhancing grid visibility also. And because of this higher speed scan rates, they can capture dynamics of the system. So they are much better in comparison to the conventional SCADA system. So this is the difference you can see here. See, so this one is our SCADA measurement. So see this much dynamics is missed if we are using the SCADA measurements. But with PMU, all these dynamics we are able to capture it. Okay, so this is giving a very good resolution also. So this is nowadays. These are anyway. We have like about 2,000 PMUs have been deployed over India. So we have a good amount of PMUs placed over the grid. So now we will briefly see about the wide area monitoring systems. So wide area monitoring systems basically this is based on like synchrophasor technology. So it is considered as the heart of WAMs. Okay, so you can see you can have different generators, and though we can put it at different buses, but here we are simply showing that if we have like different buses, we have placed these PMUs. So they are measuring. They basically PMUs provide phasor value of voltage and current waveforms, and frequency as well as rate of change of frequency with an associated time stream. So the main thing is in SCADA we were not getting these phasor values. We were simply getting the magnitudes of voltage and currents. Okay, but here we are getting these phasor values, so it simplifies many of the things. So it is giving you the main measurements provided by the phasor measurement units are phasor values of voltage and current waveforms, then frequency and rock-off. So they are all associated with an associated timestamp, and this timestamp you can see it is all synchronized with the GPS. Okay, so they are measuring, all of them are measuring at the same timestamp. So you are getting a very clear snapshot of the whole grid. And the higher they provide data also at a very high speed, so it varies from 10 to 100 samples per second. So I think in India we are using it at 30 samples per second. And this time stamping, so it is allowing synchrophasor from different utilities to be time aligned. So this is how at the same moment you can capture what is happening in the entire grid. Then accurate GPS time stamping allows voltage phase angle differences to be compared at two different parts of the grid. So you know that these voltage phase angles, they are basically indicator of the stress on the system. So if we are getting earlier, like we were using state estimation, we were getting voltage magnitudes and current magnitudes and power and reactive power measurements. From those measurements, we were using like state estimation to obtain the phase angles of the voltage at different buses. So now we are directly getting the phase angles at all these buses, and the phase angles, so one will be the reference, and then you can monitor this phase angle differences easily, which will actually reflect, if you are monitoring these phase angle differences, it will reflect the stress on your system. So it becomes quite easy to monitor these things. Now, this is a typical WAMS architecture. So you can see that we have like different substations where we are placing these PMUs, and they are all synchronized with the help of GPS system. And these data are being transmitted to regional load dispatch centers. Okay, and there we have PDCs, phasor data concentrator, which are basically aggregating the data from all these PMUs, and then they are time aligning this data. Okay, so these we have their PDC, and then we need to perform certain data analytics and visualization techniques to understand what is happening in the grid. And then these data are also sent to National Load Dispatch Center, and again they have this facility. Okay, so it is like everywhere we are having like PDCs, the regional level also, and then national level also, and then we are analyzing this data received from all the PMUs. Now, synchrophasor analytics have different applications. Okay, so they are providing voltage and current phasor, frequency, and drop-off. And with the help of these parameters only, we can like visualize the entire power grid. So that is why we call it a wide area visualization. At the National Load Dispatch Center, they can easily monitor the entire Indian power grid. And we can have frequency monitoring, because the frequency is a parameter which reflects about many of the things in the system. And then voltage stability monitoring also. So we need to develop actually the algorithms to utilize this large number of data which we are receiving from PMUs, that how we should monitor voltage stability monitoring and in the required way. So that needs to be developed. It is there, but still some improvement efforts can be made to improve them. Then if certain oscillations are happening in the system, then we can detect them that oscillations are happening, because these oscillations are problematic. If these oscillations goes on increasing, then it may cause instability. So it is important to identify the oscillations and their source to take precautionary actions. So this can be developed. Then if any kind of event is happening in the system, we can detect and create alarm. And this angular separation, you can see that once this angular separation it is increasing, so it is telling us that there is instability going on in the system, so something can happen. So now we'll see synchrophasor database event detection. So now this signature analysis is there to identify the event. Like this is actually frequency. So with the variation of frequency, we can see that it indicates, but we are when we are seeing this window, we are able to understand that there is some event happened. So like the first one, if you consider, there is a dip in frequency. So dip in frequency, it means that there could be a generation trip. Okay? Or yeah, there could be a generation trip because the frequency is going down. If this is a very short transient is coming, it could be due to fault. So there are certain kind of signatures which tells us about something. But what we want from this, that as soon as this event is happening here, we should be knowing about this event as quickly as possible. This is from this window we are able to see that this event is, this kind of event could be there. Okay, but we would like to know in practical real time when if some event is happening, we would like to know as soon as it is happening, so that we are ready to take, we know what is happening in the system, and we are ready to take any preventive actions required. So with this intent, we have developed one method where our objectives was to detect events which are having both fast and slow dynamics using wide area frequency measurements. So we have utilized only frequency measurements to identify that if some event is happening, that event is with fast dynamics or slow dynamics. And it is also possible, it is not necessary that only one event is happening at a time. It could be like multiple fast events, because multiple lines can trip. Fast events means it could be transmission line fault or some line trip is happening, that will be considered as the fast event. But if like we are saying that the slow dynamics, then it could be like generation loss or load loss. These kind of events could be events with slow dynamics. So it is quite possible that we can have multiple line trips. So multiple fast events are happening, because sometimes it is cascaded line trips. So one by one lines, because of overloading, they are tripping. So that also should be captured. So we should be able to capture multiple fast events, slow events, and multiple fast events occurring during an ongoing slow event. If already some slow event is going on, like suppose you say that there is a load loss, and during that load loss, the system is still going to the transient this changing conditions, and that time some line has tripped. So during this ongoing slow event, a fast event is also happening. So we should be able to recognize that also, because then only it will be able to enhance the situational awareness. Further, we wanted to our method to have low computational complexity, so that it is able to be applied in real-time applications, and it should be able to detect the event right after its occurrence, means as quickly as possible. So other than this, what information we would like to have about if some event is happening is at what time the inception of the event happened, and what is its location, and how severe it is. So we achieved all those things with our method. So basically, we used this variable distribution based method, where this probability density function can be defined like this. And here the B and C are the like scale parameters and the shape parameters. So we can see these are the important parameters, though we have three parameter variable distribution also, but we have used two parameter. And you can see the plot that if this B scale is changing, but shape is fixed, because we have keep C as fixed at 3. So this is only, this B will affect only the scale. But here you can see that if we are B, we have kept constant, but C we are changing. So C is changing, so it means it will change the shape. And that is the basis of our method. So this C is used to identify the event in our method. So you can see, so we have utilized only frequency measurements. So the cumulative distribution function for frequency measurements can be represented by a two parameter variable distribution as this. And we have like linearized this CDF so that we can estimate these parameters. So by linearizing this thing, we finally obtained this, which is basically a equation of a straight line. So here B is the scale parameter and C is the shape parameter. So this C shape parameter, it is giving an indication for the event detection. So now we'll see the plot. So we had some event data. So steady state operation was there, and the steady state data was also used, and then we plotted this log of 1 by 1 minus fx and versus log frequency from the like previous equation. You can see, so we have plotted this versus frequency. So B has the same parameter as x. So we observed that during a steady state, this C is tends to be 90 degree. So this is one thing, that if there is a steady state, then this C tends to be 90 degree. But if some event happens, then the C will deviate from this 90 degree. So this gives an indication that event is happening. Now, so to make our reference easy, what we did, that we have defined another parameter which we are calling as gamma or variability, and we have just shift the reference from 90 to 0. So this variability we are defining as 90 minus C. So during operation, the C tends to 90 degree. It means that variability tends to 0 degree. So if variability is 0, it means it is steady state operation. But if it is increasing, it is becoming positive. So then it means that an event is happening. And the severity of the event is directly proportional to variability of this measurement system. So that is the basis of our method. Now, to identify this variability, to calculate, we have used dual window architecture, because this frequency measurements we are receiving. So what we considered, that this small window is also there and this big window is also there. So this small window we have used to identify events with fast dynamics, because what happens now, if you have events with fast dynamics, the dynamics, like the values will change and then they will come down, as we have seen in the signature analysis one, that if it is transient, it is quickly coming down to the previous values. So if we take large number of samples there, then what will happen, the variability, it will go down, of the samples will go down. So we have taken this small window where we are considering that only 5 samples are received. So this 5 samples we have considered in the small window, and for the big window we are considering 250 samples. So variability is computed for this small window as soon as this 5 samples are received, and for every time we are receiving 5 samples, we are computing this variability for a small window and the variability of big window. Okay. So like here you can see that this is the small window. So as soon as these 5 samples are received, we are computing the variability of this small window, and this will compute the variability of big window, and then it will be constant up to here. Then again, as soon as this 5, we are coming to this here. So as soon as we receive this next 5 samples, we are computing the variability of a small window and then the big window also. So every 5 samples, we are computing the variability of small windows as well as big windows. Okay. So 2 windows, why we have considered this is because we found that the variability of the frequency measurements during events with fast dynamics is more sensitive to the small window size. Because if we are having more samples, then obviously if it has settled down to steady state, those steady state samples will push down the variability. Okay, and then it will indicate that no event has happened, so we can miss the event. So but this small window, this events with fast dynamics were found to be unaffected with big windows. And for the events with slow dynamics, we found that because the dynamics is being slow, you need to include more samples there so that the variability crosses a threshold. So that is how we decided. Now, this small window size, so you can check here that we are having this window. So this is a transient event, something is happening. Okay. Now we are computing for the 5 samples. We are computing the variability of small window and variability of big window. So we have set some threshold. I'll come to that little later. But we can see here that as soon as this transient is happening, so this is we have frequency measurements from two places. So this small window variability is exceeding, which is indicating that this event is happened. But because no slow event is observed here, this variability remains below the threshold. Okay, so to separate the fast event information from the post event steady state samples, we are using this small window size. And again, one more thing is why we have come to 5 samples, because we have considered like the sampling rate is considered here in this method is 50 samples per second signal. And we are receiving with this sampling rate, we are receiving 5 samples in 5 cycles. So usually it is observed that the fast events, they usually last for 5 to 10 cycles. So that is also one of the reason to use like this with 550 samples per second signal, we can use 5 cycles so that the fast events is lasting for at least 5 cycles and we are able to identify it. Now, big window size. So this figure shows you event with oscillation. So it is like a slow event. Okay. Now you can see that when we are computing the small variability for small window and big window, this small, because no transient event is there, it is not crossed. The threshold is not crossed. But for the big window, as soon as this is happening, so this is telling you that some slow event is going on. So if we use very large number of samples, then it is quite possible that it may give to inflated values of variability, because even after the event has settled, you are using those measurements to give to come into the picture of like variability while computing it. So it may give false detection. And if we reduce the number of samples, then quite possible that the dynamics of event may not be captured. So it is important to identify that what should be the sample size. So we have selected that a window size of 250 samples will be there. So basically for big window, we have decided that 5 seconds should be there for 50 samples per second signal, or whatever sampling rate you are considering, at least 5 cycles should be 5 seconds should be, the window should comprise of 5 seconds. So now, but we have also observed that we have considered here 50 samples per second, but it is not necessary that you are getting the samples at 50 samples per second. So it is quite possible that you are receiving PMU measurements at 10 samples per second or maybe some other. So that will affect the performance of our method. So it is quite clear that if you are improving the sampling rate, obviously the detection resolution will be very good. But if you are reducing it, it can identify, we actually observed it, that if we are reducing, then it may not be able to capture the fast events, but it will definitely be able to capture the slow events. So you can see here that 10 samples per second, all these are like fast events which are happening. But when we are using this 10 samples per second, so these events are missed here when we are using 10 samples per second sampling rate. Okay, so it can miss the fast events, but slow events it will be able to capture. So the lower sampling rate may miss most of the fast events, but still capture the slow events effectively. And irrespective of the sampling rate, slow events can be detected, but for detecting fast events, we identified that the sampling rate should be greater than or equal to 25 samples per second. So, and the event detection resolution is obviously, if you have higher sampling rates, this will be better because you will receive those samples, the required number of samples, quite fast. So this is the complete methodology, like how this algorithm will work. So in phasor data concentrator, we will be receiving the measurements from different NPMUs, and then we are time aligning those measurements here, and we'll see here that incoming frequency samples populated in the kth small window. Now, so first of all, we'll check that the data for latest 5 samples is received or not. If it is received, then we can like it is received, then we can interpolate missing data in the kth small window, if any, because it is quite possible that sometimes some samples are missing. So if there are any samples missing, we are interpolating that missing data. But if suppose we are receiving NAN for consecutive small window, 5 consecutive small window for ith stream, then we are considering that PMU to be offline. Then we cannot do actually that time. So once we have like identified all the measurements are there, like 5 samples are there, we are calculating the variability for a small window, and then we are checking that if the variability of a small window is greater than the threshold. If it is not greater than threshold, then no fast event is detected and we are moving to the another window. And here also, if we are checking that it is not greater than the threshold, we are going to this calculating big window, variability of big window. But if it is greater than the threshold, then it says that event is there. So fast event is detected. Then we compare that where the event is located. So we will see for all the PMUs, this variability will be compared. So whichever PMU is having the maximum value of variability, there the event will be located. And then because that window already contains the data with fast event, so it will interfere with the slow event. So that time what we do, we remove those samples from the kth big window, and then it will be done with 245 samples, not 250. So we'll calculate this variability of big window, and then again we check that if it is greater than threshold, no slow event is detected. Yes, then slow event is detected, and it will be located at the PMU, which is having maximum value of variability. So then this alarm can be triggered. So this is how this whole method works. Now, we also wanted to take into account, because there could be sometimes communication delay in the network. So we want to design a method which is able to tolerate this delay effectively. So we observed that usually the typical values for the transmission delay between PMU and PDC are between 20 to 50 milliseconds, which is about 1 to 2.5 cycles. And we have defined that time to receive 5 samples, it is referred as the trigger time. So depending upon the sampling rate, this trigger time will differ. But we have defined as soon as we receive the 5 samples, that is considered as the trigger time. And the computational time for this variability of a small and big window was like a combined processing time is 0.25 to 0.5 cycles, okay, on an i5-8250U processor with 8 GB RAM. So we have defined their delay margin. We want to keep certain margin, okay, that if the data is coming little bit late, then how much, then also we should be able to proceed. So we define this delay margin as the difference between the trigger time and the computation time. Okay. So with this different sample rates, we have here like big window, I told you that we are considering the window size as 5 seconds. So with these simple sample rates, with varying sample rates, we will obtain this many samples in the big window. And trigger time. So if it is 10 samples per second sampling rate, then 5 samples will obtain in 25 cycles. If it is 25 samples per second sampling rate, then 5 samples will be obtained in 10 cycles. So these times are given in cycles. And then we are subtracting computation time from this trigger time. So we are getting this delay margin. So we can easily see that, if you are increasing the sampling rate, your detection resolution is becoming very good. But at the same time, your delay margin is reducing. Okay. So that is the problem. So if you have very low sampling rate, delay margin is quite high, but detection resolution is not good. So actually, a good event detection technique, it should be able to have a trade-off between this, to account for this trade-off, like trigger time and this delay margin, detection resolution and delay margin. Okay. So what we did that, let us consider that this trigger time is same. Those sampling rates are different, but trigger time we have considered same, that it should be 5 cycles. Okay. So if we are reducing here trigger time and this computation time is this fixed, so delay margin is also good. Here like delay margin was less, but here we are able to maintain, because this 5 cycles is kept as the trigger time. So we are receiving 10 samples. We have increased the samples here. So by analyzing all those things, we come to the conclusion that it is better to have 250 samples in the big window and 5 samples. Let us keep this trigger time fixed at 5 cycles. So this has been used in our method. Now, how to decide the threshold? That is another important question which needs to be answered. Okay. So what we considered, actually we have analyzed different archived data for the events, and we found that there is a positive correlation between this variability of a small window and change in frequency. So usually it is seen that for the fast event, this change, the frequency actually it will vary. The change in frequency will be from 0.03 hertz to 0.25 hertz, depending upon the severity of the event. Okay. So this change in frequency, it is reflected in the variability of the small windows, and here you can see. So obviously, if the it is better to have the lower bound of this. So 0.03 hertz is found to map with 0.02 value of variability. So we have selected the threshold for a small window as this F represents here fast events. So threshold for this small window is considered as 0.02. If it crosses that value, then it means there is a fast event happening. Now, when we observe this for slow event, we observe that if some slow event is happening, then there will be a change in the slope, okay, of this frequency. So this slope was identified, and this value is considered at 0.03 hertz. That if there is a change in slope which is greater than this within the big window, then it indicates that some oscillations are going on or some slow event is happening. So similar kind of analysis was done, and then we identified that the threshold for the big window should be selected as 0.007. So this is how we have identified that if the gamma variability of a small window is greater than gamma f, which is this, and variability of big window is less than gamma s, this is fast event. If gamma SW is less than gamma f and gamma BW is greater than this threshold, so it is a slow event. Then if both are there, both are crossing the thresholds, it is fast event also and slow event also. If both are within the threshold, then no event is happening. Okay. So now we'll see different kind of events and how we identified that. So this is events with fast and slow dynamics occurring separately. So these are the measurements recorded by the PMUs placed at Mumbai and Kanpur. So you can see here, these boxes like this one, this box A, and this one is showing the fast event. But this one is showing you the slow event. And you can see the variability here. Whenever these fast events are happening, this is crossing. This gamma SW is being crossed. It goes above the threshold. Okay. And when this slow event is happening, so this only gamma BW, the big windows are triggered. So we can easily see that when the transient events are happening, that time only small windows will be triggered. But when the slow event is happening, that time only big windows will be triggered. So the computation time for this was found to be 0.045 to 0.05 cycles, and or 0.9 to 1 millisecond. And for big window, it is 4 to 5 milliseconds. So, but because we have kept the trigger time as 5 cycles, we are receiving, and as soon as we are receiving these samples, we are able to detect the event. This is the zoomed version of this plot, so you can easily see the variations here for the slow event also and for the fast event also. Now we have a power swing event. So this power swing event occurred near Kanpur region on about April 15, 2011. So it was accompanied with swings in the frequency measurement. So though the event initiated at Kanpur, but because our grid is electromechanically coupled, so its effects are seen at Kharagpur also. Okay. So this is the fast events which are captured here, okay. And then this the slow events we can see here. Now you also notice that this is because the Kanpur variability of PMU placed at Kanpur, it crosses first here also. So it is showing you that the event occurred near Kanpur. and the timestamp at this moment. It shows you the inception of the event. So we are also knowing, and with the how high this variability is going, that will tell you the severity of the event. So with this single parameter like variability of the frequency measurements, we are able to detect the event, its time of inception, its location also, and how severe it is. Now, this is an islanding event. So this islanding event was observed on 25th June 2014. And it was, I think, near Suratkal. So it was there. So southern region, it's separated from the rest of the grid because this frequency is going down. And here the frequency, at the Kharagpur side, the frequency is increasing. So this is telling you. Now you see how big this thing, because islanding has happened. So it is a severe event. So you see the variability value has also increases. So the big windows detect the presence of an event within 220 milliseconds after the inception of the event using the PMU placed in southern region. Then we have a tripping of like 800 kV HVDC line event. So it was a very fast event, but we were able to capture it. You can again see the big windows were not triggered here. Only there's a small windows were triggered. Now this is an oscillatory event. So this oscillatory event, again, you can see that here, this Mumbai, the measurements received from Mumbai and Kanpur. So only this big window is triggered here. So we were able to like validate this, that okay, our method is working well on different kind of events which usually happens in the system. Then this was a slow event co-occurring with fast event. So both the events were happening. So here, like it is slow event is happening here, but the fast event is happening at this slow event is already going on, and during that fast event was triggered. So this was actually the event happened near in Gujarat actually. So this Western WRLDC reported a generation and load loss near Mundra on 12th March 2014. And here the frequency dropped by 0.67 hertz. You can see here. So these transient events are detected due to the independent dual window architecture of the proposed method. So that is the necessity of this dual window architecture. Now, it is also important, we have seen that this principle or this concept is working well for different kind of events, but we need to compare its performance with the other existing methods as well. So we have compared our method with the other existing methods. We have compared it with 4 different methods, which is like Tiger-Kaiser energy operator based method, which basically computes the signal energy. And if it is crossing a threshold, then an event is identified. Then Mahalanobis distance based method, where like we have candidate window and a parent window, and we use to compute this MD distance between the two. If it crosses the threshold, then the event is found to happen. Then in principal component analysis also, we are basically using historical data with the measurement set available, and then some reconstruction error is also developed. Based on that, we identify that the event is happening or not. In standard deviation based method, we are computing the standard deviation of like Rokov and phase angle deviations. So based on that, we are identifying. And then this is Vito is variable based excursion, transient and oscillatory method. So this is the proposed method. Now, for the event which I have shown recently, like generation and load loss event near Mundra. So a generation loss of about 3,800 megawatt and load loss of 1,370 megawatt was there. Now you see, this is like Tiger-Kaiser energy operator based method. So they were not able, all these other 4 methods, they were not able to distinguish whether it is a fast event or slow event, but they were simply identifying that event is happening. So we are simply representing them if they are identifying fast event. So like this. So we can see the event is happening here, and it should start occurring from here itself and here also. But during this portion, it is misdetecting. The event is going on, but it is not able to identify here because this cross nominal, it crosses the nominal frequency range after the inception of events. Then this method is not able to identify the event. Okay. Then this MD method, if you see, so it is also misdetecting. Then here the event is happening, but it is not able to identify it. Then this PCA also, it is identifying little late. The event has started happening from here, but it is identifying it here. So it is delayed detection. Then this SD-based method, it is detecting the event here, but the fast event occurring here is not able to be identified. But if you see the proposed method, it is able to distinguish between the slow event. So this is all slow event going on. And here, both fast event and slow event are happening. So we are able to distinguish it. And other important thing is it is having the least delay, and it identifies the event 340 milliseconds faster than the SD method. Now there is multiple fast and slow events near Mumbai. So again, you can observe here that this TKEO method, it is always detecting that event is happening, but it is not so. You can see this one, we have compared, actually, when we have analyzed it, we have compared our observations with the reports uploaded on the corresponding RLDC centers. Okay, so we have verified our results from there also actually. So this is like no event is happening here, but it is always identifying that event is happening. Okay. So it is falsely detecting the event because the measured grid frequency is lying well beyond the nominal range. Then this MD method, it is detecting the slow event. It is this slow event is happening, so it is identifying it, but it is prone to misdetection. Then PCA method is also identifying all the time that event is happening. Then this ST method, it is identifying it here, but the problem here is once this, see, you can see this also, there is these blue are represented by the fast event, but in between there is no fast event, but it is identifying there also. So it is also misdetecting the event. Then there is multiple element tripping near like 400 by 220 kV substation in UP. So it was at Muzaffarnagar. So this fault occurred at 220 kV Muzaffarnagar Nara line, and delayed fault clearing. Because of this delayed fault clearing, 400 by 200 kV transmission lines were tripped. Okay. So this is that event, but this TKEO method, it will detect an event at the measured frequency crosses 49.92 and 50.08 hertz range and has misdetection. So it is not able to identify with this nominal frequency range. Then MD method is also unable to locate the fast event. Na? The fast event is happening here, but it is not able to identify. It is only identifying here. Then this PCA is also unable to identify any event, and this SD method is unable to detect the fast events which are happening here, but it is only identifying this slow event. Then failure of current transformer at Samaipur. So again, you can see this is all like slow events are going on. Okay. So this method here, TKEO method is misdetecting it. Then here also it is like misdetection for this MD method. This PCA, so it is giving delayed detection. And then the events start happening from here. So it is also detecting event at little later. Okay. That is the problem. Now, basically, when we have verified it at Indian Power Grid measurements, it was important to see its performance for some other grid also, because different power grids exhibit different characteristics. So it was like North American grid disturbance, where they have deployed like FNet or Grid I, which is a low cost, quickly deployable GPS synchronized wide area frequency measurement network. So these data were available on the website, and they have deployed like 100 FNet devices to measure the grid dynamics at a resolution of 10 samples per second. So we are considering here only slow event. So this a generation trip event occurred at this time with a loss of 500 megawatt at the WECC interconnection. And the event occurs near Calgary unit. So you can see, though we had measured this data from 28 generating units, but we are considering here only 7 generating units. So you can see this variation reflects that some event has happened. So this big window is reflected, and the event, this unit 1061 is representing Calgary only. So this event is happening because it is the first one to cross the threshold. The event is happening near Calgary. Okay. This is the thing. But one more important thing which we identified was it could be sometimes like frequency ramping event is happening, which is because of some schedule changes in the system. Okay, so then that should not be confused with some event. So how to distinguish this thing? So we have identified this event also from the this Eastern interconnection. So these are the frequency measurements. And when we computed the variability of big window, it was found to cross this variability. But then how to distinguish it? So its shape will indicate that whether it is an intentional event or some frequency ramping event is there. Okay, so because all the units are having similar kind of shape, so it tells you that it is actually a intentional event, or it is due to scheduled or planned scheduling. Okay, so this similarity of the shape of variability of big window of all the units may help the operator in distinguishing between a fault and a ramping event due to the predetermined scheduling. Here when the event happened, uh, it was like the shape was different for all these units, but here it is same. So now we can conclude this presentation that so we were able to define a single parameter variability which was able to detect and differentiate between fast and slow events and identify events at nominal and off nominal frequency at its location in near real time and quantify its severity as well as identify the event's inception time and location. So the proposed method also overcomes the disadvantage of the existing event detection techniques such as misdetection, delayed detection, false detection. The architecture of the proposed method ensures its feasibility in near real-time operation as it offers a low computational burden, handle missing data, and communication delays of up to 90 milliseconds. And it is able to work with different sampling rate also. So this method would be beneficial to the system operator in visualizing a better situational awareness about the events and would be suitable for event monitoring of a practical system. So with this, I would like to thank you, and I think uh, we can take question answers now.
Thank you, ma'am, sir, for such a detailed explanation of wide area measurement systems and its application in dynamic event detection. There are lots of real-world examples which might have helped our audiences to learn the topic better. I will take up some questions from the chat box, which the participants had already posted. First question is asked by Sunil. Ma'am, what is the minimum redundancy of PMU is required in wide area measurement system for reliable event identification?
See, actually, usually we consider as the system should be observable. So that you have to see based on like what applications you are considering. So see, it happens that we when we have utilized actually limited data which was available, so Kanpur and Kharagpur, but see the event actually it happened, it was simply telling us that event happened near Kanpur, but actual location may be quite far from Kanpur also. It depends if we have PMU locations installed there also. So we cannot define as such like what minimum number, but it will give as you can consider that it will increase the accuracy of the location. Event has happened that you can identify, but I think if you have more number of PMUs, then it will help in identifying the actual location.
Okay, I hope this answers the questions. And next question is asked by Jitender. He is asking, okay, though the acquired data is time-stamped in WAMS, still different location data may have different different location data may have different delay association with them.
Yeah, but they'll come with timestamp, isn't the data may have this delay, but they will come with the timestamp. So when they are coming with the timestamp, we are aligning them according to timestamp in the PDC. So that is why now if there is like when we are organizing, when we are collecting the data, we are checking that it is there or not. Suppose it is not there, it is delayed due to that, but that time we will consider it as missing, so we can interpolate it. and then we can use it.
Subham is asking, ma'am, I would like to know about the application and challenges challenges associated with the micro PMU in event detection.
Application, I think application I have already shown. I think challenges is all like it could be what I can see. It could be all related to pardon.
Himanshu, can you please, Himanshu Maiti, can you please mute yourself?
Yeah, so challenges associated with the micro PMU in event detection. I don't think so, because the if the data are available, then it is all is like you how fast your algorithm is working and is able to deal with that kind of data. So I think it should be capable enough. If we our algorithm especially, we saw that it was able to handle those things. So I don't think like any challenge with event detection specifically after this.
Okay, we have the last question from Anamika. Can MIAL algorithm be used to reduce the computational time?
You can use it, but I think, see, then the reliability now with AI and ML algorithms, what happens? The reliability needs to be important, isn't? And we have with the problem with this AI and ML algorithm is once you are the testing data is different from the training data, then it becomes difficult to rely on them. They will not be able to perform well. So when this like there could for event detection, there are different methods which are proposed. They are based on like signal processing methods or this optimization based methods also, and then some statistical methods. Though they have performed very well in identifying this event. As you can see, like we have when we have used these 4 other methods, they were all very fast. So that is the reason we compared our method with those methods. So I only have this doubt, like that how good this AI algorithms will be performing. So reliability could be one issue there. That if they are falsely predicting or missing any important outcome, then it will be a problem.
I think there are no any further queries. So thank you, ma'am, for your valuable time with us. Now, on behalf of IEEE SBC at IITK, I would like to present you a token of appreciation. Ma'am, please accept the token of appreciation.
Sure. Thank you.
Thank you.
Thank you.
We'd like to have you in the future editions of PERA also.
Yeah, sure. It is always pleasure to do something for our alma mater.
Yeah, thank you so much.
I leave now?
Yes, ma'am. Tomorrow we'll have the session, morning session at 10 a.m. and it will be by Dr. Anamika Dubey. So we'll be delivering the expert talk. Thank you. Hope to see you all there.